Hello guys, in this video I will show you a modification of my Diamond SD330 screwdriver antenna to be self-adjusting. It is my base station antenna in my apartment for several years, mounted on the terrace, and now it is like it should be. So what I can do now is I go to any frequency on my ICOM 7300, wait some seconds, and the antenna adjusts itself to be resonant on this exact frequency without tuning it or pushing any button. It also drives about 3 times quicker than the original one. I can also enter a frequency and the antenna drives to the exact necessary position. The original Diamond SD330 screwdriver antenna has a simple motor with a gearbox in it. You can drive the built-in coil to one direction or the other. If you reach the bottom, a switch interrupts the driving down direction. If you drive too much up, it just jumps over the end of the threaded rod. Very simple but solid construction. I was always wondering why they don't put the stepper motor in it, so that you can track the position of the coil. I guess costs are the reason. I disassembled the antenna and took some measurements. The shaft of the motor or the gearbox, what connects to the threaded rod, is 4 mm in diameter. There is room for a motor about 28 mm in diameter. With that 2 dimensions written down, I looked up what stepper motor exists and I found a NEMA 8 motor has a shaft diameter of 4 mm and are only 20 to 20 mm wide. Awesome. I ordered the biggest, not too expensive NEMA 8 I could find because I had some doubt the power of that little motor will be enough. I then 3D printed a new mounting plate for the NEMA 8 and the motor was in place. The already built-in switch in the SD330 I used later to detect the lowest position of the coil with the microcontroller. That switch will be important to calibrate. On my breadboard I made an antenna controller circuit with a Raspberry Pi Pico 2W microcontroller, a small display, 2 buttons, a rotary encoder, 4 LEDs, and the A4988 stepper driver board. The cool thing is, the Pico 2W has built-in Wi-Fi. So instead of laying another control cable to the antenna, I connected the antenna controller to my local Wi-Fi network. It will be controlled via simple UDP packets, what you can send from your computer, your phone, everything what is connected to the local Wi-Fi network. After testing it on the breadboard, I painted the schematics into the computer and ordered a PCB of the circuit. I added also a simple field strength meter circuit to it. I wasn't sure if it will work. More to that later. So a short description of the circuit. This is the printed board. Like I said, here is the microcontroller, the Raspberry Pi Pico 2W. This costs about, I think now, €8, one module. This is the stepper driver A4988. It costs about, I think, 3 pieces, I'm not sure. Also 3 pieces, I think €10, something like this. We have here 4 LEDs, we have 2 buttons. Here's the rotary encoder. Here is a step down converter. The 12 volt comes here in. The 12 volts is going here in, then there is a fuse. It goes to the step down. The step down converts from, here comes so around 13 volt from the battery. Will be converted down to the voltage what the motor needs. The motor runs best between 6 and 7 volt. So the step downs converts down to, I think I made 6.7 volts. It's what you made with this with the resistor divider. So it was 6.7 in my case. This is going directly to the stepper driver, and for the peak to power the Pico I have here a voltage regulator for 5 volts, so it converts from 6.7 to 5 volt, and this 5 volt goes to this Pico 2W, 4 LEDs, 2 buttons. Here's the rotary encoder, I have it here on this printed board, but I not have it on my antenna controller on the outside. I not need it. Yeah, this and here we have here I added this field strength meter. This is more or less just a rectifier circuit for HF frequencies, and with simple diodes. I just used 148 diodes. Those very simple diodes, very cheap. This is really working great. The display. Here is the connector for the display. I choose this display. This is a simple TFT 1.77 inch 160 to 128 pixel. It has I don't know how much, so you have red, green, blue colors. You can mix this. This is driven with the SPE interface. I think I have it adjusted to 9 megahertz, so quite fast. Yeah. And how the stepper is working in general. So you putting out a pulse wave modulation signal here to the stepper driver with a certain frequency. The frequency, it defines the speed of the motor, and you give the driver board also the direction, the motor should turn. What you're doing here is, or what I'm doing here is, this the PWM signal what goes out to the stepper driver is going back into the microcontroller, and I count every step what I take with the microcontroller. So every pulse from the PWM signal will be counted by the microcontroller itself, and so I can perfectly stop the signal when my step count what I want to reach is reached. So yeah, this is how I did it, and you're not losing any steps on this side. So the motor or the driver, this is not a closed loop. You can buy stepper motors with a built-in encoder, and so the stepper driver takes care that the motor is not losing any steps. This is here not the case. This is just a simple cheap motor what I used. I think it's not really necessary, because this is not really super precise, or not a CNC machine or something like this. Yeah, I think this was more or less the main. I also measure, this HF field strength signal I measure with a ADC, so analog digital converter from the Pico. Yeah. Designing a housing for the antenna controller was next in my to-do list, besides writing the software. The housing has a small antenna for the field strength meter. The antenna for Wi-Fi is on the Pico board. On the bottom, a temperature sensor protrudes from the housing. So it's also a small weather station. I was worried at 100 watts something so close to the antenna would make problems, but so far I not had any interference problem between HF and Wi-Fi. Let me show you now the ST330 antenna controller in use and how it operates. I can use my ICOM 7300 like I have an antenna who is resonant on all bands, or let's say on all bands what the antenna can handle. The antenna can be resonant from 10 meter to 80 meter. So let's switch to, we are now on 21 megahertz. I will check the SWR. Here I'm powering 16. Look at the SWR here. 1.5 here. And now we are showing the scope. I switch now the frequency to 14 megahertz. And look at the spectrum. The spectrum will, oh wait, let's see, we are in the spectrum. The spectrum will be first black and will then show all the noise coming because the antenna is adjusting. I will go here, it's more or less black. Antenna is driving, I hear it even with the open window, and now it is tuned. This was it. So in the higher bands this is quite fast. And I will prove you this. That it's resonant. I measure the SWR. Look at this value. 1.8 I have here. So what I'm doing is I go now to 40 meter. Everything is black and now the noise is coming, the antenna is adjusting, and here we are. It's quite fast. I will measure the SWR also with quite low meter. Look at the SWR. SWR is 1 perfect here. It's not, the antenna is not everywhere perfect. On the lower, also on 40 meter, it's working great. So let's check it on 80 meter. Go to 80 meter. The antenna is driving, I hear it. It's extremely a lot noisy in Vienna. It's nearly unusable, this frequency. I hear it driving. It needs from 40 to 80 meter. It needs time, more time. So now it's adjusted. Let's check the SWR. Yeah, I would say 1.3. And this also works if you just dial the VFO here. It's locked, sorry. So if I dial here, I don't know, so 3.5, the antenna is driving a little bit and adjusting itself. I'm driving down, antenna is driving and adjusting itself. Yeah, and how this is working, how this is automatically adjusting itself, I will show you. So how did I do this? On the ICOM 7300 is connected via the USB port a Raspberry Pi. And what you see here is the Raspberry Pi, the screen of the Raspberry Pi. And on this small computer runs a Python script, and this Python script sends every 5 seconds or so, or 3 seconds, I'm not sure, a command to the ICOM 7300 and asks it on which frequency it's on. Then I get the frequency back from the ICOM, so I know the frequency the ICOM is tuned in. Doesn't really matter if you dial the VFO or you are switching with the button in the menu to another band. And when I know the frequency, I look up in a table what I created before. And in this table stands which position of the antenna correlates to which frequency. Short interruption, I wanted to show you how I made this lookup table, which frequency correlates to which step, to which position on the coil. So you are just tuned into this 30 megahertz and looked where at which position it's resonant. So it was on position 580. I made the same for 28 megahertz, blah blah blah. Also over all these frequencies I made this. If you're on the higher end of the frequency range, you not have to make this so often, because yeah, there you have much more bandwidth the antenna than on the lower. And I just wrote down frequency, which position of the coil, and made this table. Yeah, and this table What you see here on paper, I put in the Python script, and this is why the script knows to which position it should drive. I calculate also the steps in between, so if you want to drive here to 6.7 megahertz, what is in between these two, I calculate the position, what is in between. And then when I looked up this table, I know which position I need to drive the antenna, and I send the commands to the antenna. I will demonstrate this here. Now I'm standing on the same frequency, he's not sending anything to the antenna. But if I change now the antenna, you will see here a little change. There's something happening. So I changed now the antenna, also the frequency on the ICOM, sorry. And now I get here this back. I've changed to 14.086 megahertz, and the new step position is 3365. And I'm sending the command to the antenna, drive to this position. And that's it. So I have also another script running on the same screen you see on top. The hint behind this display here is also a script, and you see here the temperature on the outside. This also comes from the antenna, or from the antenna controller, 14 degrees. We have the position, what it just drove to 3365. And this HF max, this is the field strength meter, the value what I get back. Also I will demonstrate again. I will change the frequency on the ICOM. Then you see here a command, something happening in this script, and also you will see the position is changing here on top. So I changed again the frequency. He's driving already to 7092450. Position 8933 stands here, and he's already on 8933 on top. This is really awesome. I can also do start another script. I have another script, and I can say antenna drive to the frequency, I don't know, 10.1 megahertz. Press enter. The antenna drives to position 5485 and is now resonant. You see here the position on top too, 5485, and is now the antenna is resonant on 10.1 megahertz. So this is how it looks on the outside. I get every time when the blue light flashes a UDP request, a packet arrives, and this device sends back the data. Here you see the actual position of the coil. This is this field strength value. Here is the IP address from the controller, and this is the IP address from the last request. Yeah, here I can drive this manually up and down too with the buttons. Here you see the position. And this to demonstrate the field strength meter here, you see there stands 10. The maximum value it can show, this is a 12-bit ADC converter. This is 4096. And I will transmit now with, I don't know, 15 watts. So I'm transmitting with 15 watts, and what he's doing, he's measuring the maximum 750. He's showing me 750. There is no unit. This is not calibrated. This is just approximately something what you can, that you know something goes out of the antenna. So if I go to 20 watts, I'm on 20 watts now. we have seeing here 884. So this is quite accurate. Also at least you see the difference. And it can be useful to see if a connector is bad or getting worse, if the rain affects the antenna and not so much comes out anymore. The cool thing is, because the antenna is in my Wi-Fi network, I can control the antenna, of course, from any device in the network. And here I'm on my main computer, and this I used the program for testing the antenna controller. This is called Packet Sender, and what it does, it just sends UDP packages over the network to a specific IP address and a specific port. But now in this program, for example, I can get the position here. If I push here, I'm sending the command or the sentence FE E0FD, these 4 bytes, to a specific IP address. What is here wrong? Here's the correct. I will send this and get back from the antenna the position 8970, you see it here. I can ask my antenna, give me the temperature. The temperature is now 13.5 degrees. I also have a command for 3 measurements. So here I have temperature, position of the antenna, and the field strength. What you saw before on the screen of the Raspberry Pi, it was the same. It uses the same command. I can write to specific positions. I can send the command. The command is here, for example, F1, and then here the next 2 bytes are the position of the antenna. FD is always the end of the sentence. Position, I can reset the microcontroller. I can save to flash manually, but it saves the position from the antenna automatically every 10 seconds if the position changed. So if you power the controller off, the next time you turn it on, it's on the same position, it not loses this. So here's a UDP Packet Sender app on my phone. I just have to type in the correct IP address. This is the IP address of the antenna controller, and I can write here the command for, I think the position is E0. I will send this to the antenna. E0FD. I'm idiot. I must press here receiving, start receiving. So, and I get the position back 8970. If, for example, E2FD, I get the temperature. F3FD, I think, this is all what you saw before. So this is, you can do this on any device, very simple. So that was my video about the tuned Diamond SD330. I hope it inspires you a bit, and I also hope that manufacturers will provide us with slightly more sophisticated products in the future. Thanks for watching.